Hey everyone, and welcome. Today we're tackling a really interesting grid problem. The goal seems simple. We're given a matrix, a grid of zeros and ones. We just need to find out how many square subgrids exist that are completely filled with ones. Let's break down what that really means. Okay, let's walk through the first example to get a feel for it. We have this matrix here. First up, the easiest ones to count are the 1 by 1 squares. A 1 by 1 square is really just a single cell with a 1 in it. If we count them all up, we find 10 of them. So that's 10 squares to start with. Next, let's look for 2 by 2 squares. We need to find a 2 by 2 block where every cell is a 1. Scanning the grid, we can find one here, and another one right next to it. Then, moving down a row, there's a third one here, and a fourth one here. So that's 4 2 by 2 squares in total. And what about 3 by 3 squares? Looking at the grid, we can see there's only one big 3 by 3 block of all ones. So we add that to our tally. We have 10 1 by 1 squares, 4 2 by 2 squares, and 1 3 by 3 square. Adding them all up gives us a grand total of 15. So how could we write a program for this? The first idea might be brute force. Go to every cell, and from there try to expand a square outwards. But that's very inefficient. A much better way is to use dynamic programming. And the secret is to change the question we're asking. Instead of asking what square can start at a cell, we're going to ask for each cell, what is the biggest square that can end at this cell, using this cell as its bottom right corner. Let's think about what makes this possible. For any given cell to be the bottom right corner of, say, a 3 by 3 square, what has to be true? Well, first, that cell must contain a 1. But critically, the cells immediately above it, to its left, and diagonally up and to the left, must all be corners of at least a 2 by 2 square. The new bigger square is built upon these three smaller overlapping squares. This relationship gives us a beautiful formula. We can create a new grid, let's call it the DP grid. The value at any spot will tell us the size of the biggest square ending there. If the original matrix has a 0, the value is 0. But if it has a 1, the value is 1 plus the minimum of its three neighbors, the one above, the one to the left, and the one diagonally up left. We take the minimum, because the smallest neighbor is our bottleneck. It determines the largest square we can possibly form. So if we apply that rule across our example matrix, this is the DP table we get. Notice the first row and column are just copied over, since they have no neighbors to depend on. But look at the bottom right corner. It becomes a 3, because its three neighbors were all at least a 2, so we could form a new, larger square. Now for the most amazing part. How do we get our final answer of 15? We just sum up every single number in our newly created DP table. Why does this work? Think about that cell with a value of 3. It tells us it's the corner of a 3 by 3 square. But that also means it's the corner of a 2 by 2 square and a 1 by 1 square. So a value of 3 actually contributes 3 squares to our total count. By summing everything, we count every single square exactly once. Alright, let's look at the Python code. It's surprisingly short and elegant. This version does the calculation in place, modifying the original matrix to act as our DP table, which is a great optimization for space. The core of the code is these two nested loops, which visit every cell from top to bottom, left to right. Inside, we first check if the current cell contains a 1. If it does, and if we are not in the first row or column, we apply our DP formula. We find the minimum value of the three neighbors we've already calculated, add 1, and update the current cell with that new value. And right after we've calculated or confirmed the value for the current cell, we add that value directly to our running total, which we call ANS. This is how we accumulate the count. This single line handles everything. For a cell with a value of 3, it adds 3 to the answer. For a cell in the first row with a value of 1, it correctly adds 1. It's simple and efficient. So how does this solution perform? For time complexity, we have to visit every single cell in the grid, one time. So if the grid has m rows and n columns, the time complexity is big O of m times n. And for space, because we're being clever and modifying the input matrix directly, we aren't using any extra data structures that grow with the input size. This means we have a constant, or big O of 1, space complexity, which is fantastic. So to wrap things up, this problem is a perfect example of dynamic programming on a grid. The big takeaway is how changing the problem's perspective, from what starts here to what ends here, made it possible to build upon previous results. And we saw how the value we calculate for each cell can cleverly represent the count of all squares ending at that spot, making the final sum trivial. I hope that breakdown was helpful. If you found it useful, please hit the like button, subscribe for more tutorials, and feel free to leave any questions in the comments below. And hey, if you're feeling extra supportive, you can always contribute to the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next video.